Swayam Prabha. Digital India. Educated India.
Hello everyone. So our today's topic is evenness characteristics. Evenness characteristics of textile material we'll be discussing and its analytical approaches. So why evenness is important? Measurement of evenness is important for textile material. The variation in diameter or mass along the length is inherent characteristics of a textile material, be it yarn, roving, sliver, or finally fabric, which is the result of yarn unevenness. So fabric becomes uneven. So measurement is important. Now if you see an engineering material, other engineering material like rod or metal string, steel rod. So there the manufacturing process is such that the variability in diameter or mass per unit length is least. It's almost absent. But the textile material, if you see, textile material, say starting with yarn, and if we see the staple yarn, staple fiber yarn, we are concerned about the variability. We normally don't measure the evenness for a filament. Filament evenness we don't measure because the filaments are extruded from the spinneret and the chances of variability in diameter is least. It's almost absent. But staple yarn, when we produce, due to the negative control of fiber movement in the process, like in draw frame, carding, blow room, everywhere, there is no positive control. So fibers are moved, transported either by air or by frictional contact. So this results unevenness in the yarn. Also, the natural fiber like cotton itself has some irregularity in their diameter within the diameter or thickness within the fiber length. This we have already discussed. So it's important to understand the reason for unevenness, and that we can only do by measurement. So in this module, entire module, we will try to understand the each and every point, how to analyze the data, how to measure. So every aspects we will be discussing. So evenness of yarn we express in terms of either mass per unit length variation, twist variation, thickness variation, strength variation. So these are the different types of variation in yarn. So, but most popular approach is the mass per unit length variation. Why? Because all other parameters like twist, thickness or diameter of yarn or strength, they are directly related with the mass per unit length. So let us see the twist, how twist is related. Suppose we have a yarn with unequal distribution of fiber. So this is the thick portion, thin portion, thick portion. So this thick portion is generated as the number of fibers in this zone are higher than the thin portion. Okay, so this is generated due to uncontrolled drafting, uncontrolled fiber movement. So let us see how this mass variation is affecting first twist. So in ring spinning, in ring frame or in any of the spinning systems, when we apply twist, so we rotate one end. So when we rotate, the torsional rigidity of this thick portion is high because number of fibers are high. So this thick portion will exert higher resistance for torsional movement. On the other hand, in the thin portion, as the number of fibers are less, so this portion will rotate easily. So torsional rigidity will be less. So what happens? The thick portion will have less twist, and the twist will flow towards the thin portion. So that results unequal twist. This portion will be low twisted and thin portion will be highly twisted. So one can observe that higher level of twist in thin portion. So this twist variation is basically function of the mass per unit length variation. So if we measure the mass per unit length, then variation, then we can predict the type of twist variation. So twist variation is variability measurement is very difficult because in a small thin portion measurement of twist is difficult. Now what happens? So this is the fiber strand before twisting. Fiber strand before twisting. Now when twist is applied, as we have discussed, the thin portion will resist more, so twist will not be high here. So maximum twist will be at the thin portion. So what will happen? The thin portion will become much more thinner. Thin portion will be thinner than original thin portion because of the higher level of twist here. So unequal distribution of twist also impact the enhancement of the thickness variation. Although this, in addition to mass per unit length variation, so thickness variation is also measured because this will give direct visual appearance. And strength variation, suppose this is one yarn, relatively even yarn, another yarn will have this uneven yarn. The yarn breaks at its weakest point. So if we see the variability of the strength, which actually depends on the variability in mass per unit length, because the strength of yarn comes from the strength of fiber. So number of fiber, if it increases in the cross section, strength will be higher. So at the thick portion, strength will be higher, thin portion, strength will be lower. So this is directly related with the strength variability. So that's why mass per unit length measurement is most popular, although the diameter variability is also measured. Now let us discuss the types of irregularity. One is measuring the mass per unit length variation. This is called basic irregularity, that we have already discussed, because this is related with the all other type of irregularity. All other irregularities are dependent on the basic irregularity. These are the twist irregularity that we have discussed, strength irregularity and diameter irregularity. If we want, we can measure the twist, strength and diameter irregularity also. So these all are related with the fibers in the yarn cross section that we have already discussed. So this variation in number of fibers in the cross section is influenced by drafting system. So if there is any problem in variation in mass per unit length or number of fibers in the cross section, so what we do, we first change the setting or different parameters during drafting to improve the variability. So that what the target is, that to improve the fiber movement in the drafting zone. Next, diameter variability. So this diameter variability is important because its profound influence on appearance of the yarn. This is very important because while we see the yarn or a fabric, we actually see the diameter of the. So mass variability is not that important. Now let us see with one example. Suppose one yarn, it's very even yarn, somehow the yarn here, in this yarn the number of fibers are high in this zone, but this is theoretical approach just to explain. Normally this type of situation doesn't occur, as we have discussed, because when the number of fibers are more, the thickness will be more. But let us assume for the logic sake, here number of fibers are low, then number of fibers are high, lower number of fibers. Now what happens if we test this yarn mass per, for mass per length variability, here mass per length variability will be high in this end. But if we measure the diameter variability, then diameter variability is low. And finally, when we prepare the fabric, so this, there is no variation, say fabric will look very even. There is no variation in yarn diameter. So in that case, mass variability is actually not affecting here. But as I have told, that this type of situation doesn't occur in general. And one can see this mass variability, due to mass variability, twist variability occurs, and in high twisted zone, the dye penetration, if we dye the fabric, the at the high twisted zone, dye penetration is less, so there the lighter shade will be there, so that it also affects the variability in dye. So the variation in diameter are more easily perceived by the eye, irrespective of the fact whether there is a mass variability or not. But if diameter variability is there, that will be perceived by the eye. Now again let us see another condition. This condition is that by somehow during the drafting process or during twisting process, the yarn diameter is varying like this, and the number of fibers in the cross section, say 4 fibers are there, 4 fibers, 4 fibers. So everywhere we have 4 fibers. So this yarn, if we produce, and if we produce fabric out of this yarn, the fabric will look very uneven. But if we test the yarn for mass per length variability, this yarn will give you very even yarn. As per mass per unit length variability, this yarn will give very even yarn. But actually, due to some problem in drafting or twist variability, we have ultimately got this type of yarn. So this fabric, this yarn will produce a fabric with very high unevenness. So even if the mass variability is very high, very low mass variability, almost zero, because distribution ideally is equal, but due to diameter variability, as we can perceive by eye, so it is giving us a very uneven yarn. So latest models of evenness tester, we can also determine the diameter variability also, in addition to the mass variability. But in our all discussion, we will discuss based on mass per unit length variability. Because mass diameter variability is caused by the mass variability. So all these approaches, analytical approach, will be discussing the mass per unit length variability. So we have discussed that as twist has tendency to run into the thin places, variability in mass per unit length gets exaggerated in the diameter variability, that we have discussed. So twist variability also we have discussed. Variation in twist is mainly due to the mass variability, and the twist variability affects the dyeing performance of yarn. So the yarn with high twisted zone, as I have mentioned, the dye uptake will be less. Okay. So will result uneven dye. And also breakage. The soft end, where low twisted portion in weaving or in further process, so breakage takes place mainly in the soft twisted zone, which is the result of twist variation. So soft twisted portion of the yarn takes more dye, so uneven dyeing is caused by the high twist variation. Like weft bars, bands in the dyed fabric caused by the twist variability. So it is generated from the slack spindle tape jam spindles. So we can reduce this twist variability by do some modifications in spindle tapes and spindle, replacing the spindle. Strength variability, as I have already mentioned, so yarn breaks at its weakest point, and the portion where less number of fibers are there generally breaks at that point. So thin portion is the actually main cause of the yarn breakage during process. So 10 strength variability, as we have discussed. So mass variability, it depends on the mass variability. So if we see here, let us consider one yarn. This is strength of the yarn in y-axis and along the length. So we have one yarn, another yarn which is all relatively even. I will draw in a different color. So this is even yarn. If we see the yarn A and yarn B. So yarn A, the variability is very high, which gives the mean strength. This is the mean strength of the X bar A. And for yarn B, the variability is X bar P, least variation. And this variation in yarn strength resulted from the mass variability. The yarn breaks at its weakest point, not the strongest point. During processing, in winding, warping, sizing, or fabric manufacturing at loom, the breakages will take place. In this, chances of breakages will take place will be more in the weakest point. And here, number of fibers are generally lower. So although the yarn A has got higher mean strength and yarn B has got lower mean strength, but performance is poor in yarn A, which is due to the high variability on yarn strength, and that high variability is resulted from the mass variability. So if we measure the mass variability, then we can at least get some idea the performance of the particular yarn in the subsequent process. So strength variability at each and every point measurement is very difficult. So mass variability is the indication of the performance. So we have discussed the now strength variability, you can see here. So variability in strength is actually dependent on the variability in, this is mass variability. So strength drops, average strength drops as the yarn gets higher variability. So this we will discuss, this part we will discuss in detail when we will discuss the mechanical characteristics. Hairiness variability is also there, which is actually again generated from the mass variability particularly. The softer portion will create higher variability. So that affects the fabric appearance. So more light will be scattered from the portion of the web where hairiness is more. So it will get scattered. So then we will get a web band, like a fabric. So this is a fabric, and here this portion, these are the webbed yarns. This portion with low hairiness. Next portion, these are the yarns with the red color. These are the portion came from another bobbin which is high hairiness. So if you see this yarn with high hairiness portion, that will scatter light, and here there will be a regular reflection, and in the fabric ultimately we will get a band, waved band, where the lustrous portion, bright portion and dull portion. So the fabric appearance, the dullness comes from the higher hairiness. So it affects the fabric hairiness, fabric appearance in the during wearing. And high hairiness disturb warp set movement in weaving. So, and hairiness difference in the variability in hairiness can also be measured. Now, how to express the hairiness? Evenness is expressed by, one is the coefficient of variation, CV%, and CV% is nothing but standard deviation by mean, as we have already discussed in statistics part. Another expression is percent mean deviation. So what is that? Mean deviation divided by mean. So it's a percent mean deviation, and mean deviation, the expression is, this is the mean deviation, the percent mean deviation, and percent mean deviation for textile material, the strand like yarn, roving, sliver, we express is unevenness percent, U percent. Okay, this is a percent. In these two term, we express the evenness of strand, fibrous strand. And as we have already mentioned that in textile material, we express our distribution as normal distribution. So if you take the large number of data of coefficient of variation or U percent, the distribution will be its normal distribution, where statistically the CV percent is 1.25 times of percent mean deviation. So 1.25 times of U percent. So in measurement of evenness in textile material, we use this PMD, percent mean deviation, as U percent. Now coming to the limit irregularity. Now the concept of limit irregularity is that it's the theoretically minimum irregularity possible by the existing system, and minimum irregularity for staple fiber system. Suppose we have got a spinning system which is running ideal, setting is perfect, ideal condition, the environmental condition is ideal, there is no vibration, zero vibration, everything remain perfect, everything remain perfect. And if in normal other engineering material like a strand or iron wire, metallic wire we want to produce, so their manufacturing method is that we can produce one string, metal string with U percent or CV percent equal to 0%. We can produce 0% because the manufacturing method is such. We draw the metal through a particular hole, okay, some spinneret we draw. So there the diameter variability or mass per unit length variability may be 0. So this is called minimum irregularity of this system, 0%. Ideally we can achieve 0% irregularity. But in case of textile material like yarn, sliver, roving, the machines are running perfect. So, but due to the inherent process, like the fibers are in blow room, the fibers are transported through the duct by air, and where it's not possible to arrange equal number of fiber to transport equal number of fiber at a time. Similarly, in the drafting, during drafting, fibers are drafted negatively. There is no positive control over the fiber. So, it's not possible to place exactly equal number of fibers, say 4 fibers in the cross section. If I have target to arrange the fibers in equal number, it's not possible in the existing system of yarn manufacturing, because we cannot grip, we cannot hold one fiber and place at a particular place. Here fibers are drafted in negative direction. Even if the machines are running perfect, no vibration, there is no eccentricity, there is no speed variation, everything is running perfectly. Still, due to this negative control by air or floating fibers or adjacent fiber, this arrangement of fibers is not possible, equal arrangement. So there will be some minimum irregularity due to the existing system, and that irregularity is called limit irregularity. So most uniform strand of material, maybe yarn, sliver, roving, which our present machine can produce, is one in which fiber ends are laid in random order in the sliver, roving end. So sliver, roving and yarn, the fibers are arranged in the random order. So there will be some minimum irregularity possible in most uniform strand, and this is given by this relationship, where VR is the relative variance. Relative variance, and VR shows the limit irregularity. VR square is a relative variance and VR is the coefficient of variation, that is minimum coefficient of variation possible theoretically. Although we know the variance is given by square of standard deviation, but here we use variance, relative variance, square of coefficient of variation, and this is called relative variance, or in short we sometimes use as variance. So relative variance, here we will call it as variance. So this is VR is limit CV% of mass per unit length. Here we are talking about only mass per unit, and N is the number of fibers in the cross section, and Vm is the variability in mass per unit length of fiber itself. Suppose for cotton or any natural fiber, we have certain mass per unit length variation. If we measure, there will be mass per unit length variation, and if we calculate the CV%, this will become Vm, and For man-made fiber, as it is extruded, so we see that there is almost zero variability. We theoretically we consider the variability is zero here. So for man-made fiber, this relationship will be reduced to where this will become 0. So n is the number of fibers in the cross section. Now here if we see, if we increase the number of fibers, so suppose for a particular fiber, cotton fiber, if we produce for same fiber, if we produce a finer yarn, and in another case we are producing coarser yarn from same fiber, same fineness. So here there will be, in finer yarn there will be lower number of fibers, here higher number of fibers. So this will result lower variability in the coarser yarn and higher variability in a finer yarn. Now we can also see here, we are producing the same yarn count, say 20 text yarn count we are producing, and this yarn is produced from say 0.1 decitex. Sorry, 1 decitex. This yarn is produced from 1 decitex, and another yarn, it is produced from 2 decitex. So here we are using finer fiber, here we are using coarser fiber. Same yarn count we are producing. So if we use the 1 decitex fiber, so it will become, there will be 200 fibers in the cross section. Okay, 1 decitex equal to 0.1 tex, and on the other hand, where we are using the coarser fiber, so there the number of fiber in the cross section will be 100. Now if we see here, the coarser yarn with 100 number of fibers, say synthetic fiber, so limit irregularity will be 100 square by 100 for coarser fiber. For finer fiber, 100 square by 200. So we will see the finer fiber will result lower limit irregularity. So number of fibers in the cross section plays a role. We will see how the number of fibers plays a role in controlling the irregularity through some numerical. And Vm is the actual CV% of fibers mass per unit. So fiber mass per unit length variation is also important, as I have already mentioned. So this is the limit irregularity. So for man-made fiber, we have mentioned Vm is almost 0. We can consume So we can assume that the limit irregularity is of 100 square by n for man-made fiber, where variability in fiber mass per unit length is 0. Now for cotton fiber, based on large number of experimentation, the value of limit irregularity is 106 by under root n for cotton fiber. This is due to the variability of cotton. Now from this at 106 value, it's actually result of the VMC, that is variability of cotton fiber. Let us see what is the typical value, average value of cotton fiber mass per unit length variation. This typically, if we calculate, if we solve this equation where VMC 106 square by n, 100 square by n plus VMC square by n. So n will get cancelled out. So 106 square, 100 square plus VMC square. So VMC square equal to 106 square minus 100 square. So 106 square, if we calculate, it will become 106 square will be 11,236, and this will become 10,000. Now 1236, okay, and VMC will be 35.16 approximately. So from this equation we get, so the thing is just reverse. When large samples of cotton were collected and measured the mass per unit length variation, the average value was typically around 35%. For cotton it was 35%, and using this 35% here, 35.16% here, we get roughly this relations. So this is, so that's why for cotton we use this factor 106. Similarly, for wool, this is 112. Now again for wool, let us see. Hundred square by n, VM wool square by n, 112 square by n. So n gets cancelled out, plus VM square, 112 square, VM square minus 100 square. So 112 square, 12,544 minus 10,000, so 2,544, and VMW comes out to be, we see it's a 50.44%. So we can see the variability in mass per unit length of wool is higher than the variability in cotton. So that's why this factor here, in place of 106, it becomes 112. Okay. And when we blend two fibers, any two fibers, if we blend, and that results, the two fibers will have different surface characteristics, different length distribution, so different diameter, everything will be different. So that will additionally affect the fiber movement. Like for polyester, let us see, for polyester, cut polyester, the limit irregularity is typically say VR into 100 by under root NE, or VR square 100 square by NE, that we have seen for man-made fiber. And when we use with the cotton, so ideally it appears that the VR percent, this factor, this 106 and 100, this factor will be in between these two, between 100 to 106. It should be theoretically, because when we are using polyester with cotton, it should be between 100 and 106. But due to the difference in their nature, in the drafting system, they will actually behave erratically. Similar fiber, same fiber, they will behave one, at least some uniformity will be there, but here two different natures of fibers. One is surface characteristics will be different. This will result higher limit irregularity than the normal single fiber. So for blended with cotton, typically it is say 118. Say polyester cotton, if we see, this is it has been observed typically 118.8 square by N. So anyway, it is higher than the cotton even. Okay. So for wool it is 112, and we have seen the mass variation of wool is 50.44. So mass variation VM 50.44%. But wool, we normally don't measure the mass variation. For wool, it's a diameter variability is important. Where the diameter variability, here it's a VD square, and if we take the diameter variability into consideration, the relationship will become this. That means 100 square by N multiplied by 1 plus 0.0004 multiplied by VD square. This is the relationship here, and from this relationship, let us see the typical diameter variability. If we solve this relationship considering that limit irregularity is 112 square by n, and if we try to solve this relationship, we will get the VD as 25%. So if you use diameter variability as 25%, then we get this relationship. So for wool, it is assumed the diameter variability is around 25%, but mass variability is around 50.4%. So it's a typically double. Thus, for a particular fiber and count of yarn, there is a limit or basic irregularity. So beyond which our machine cannot produce. So we should actually accept the limit irregularity. We should not target to go below the limit irregularity. So that is we have to accept that fact. So limit irregularity has to be there. So we cannot produce a cotton yarn with 0% CV%. 0 CV% we cannot produce. So that's the limit irregularity. And this limit irregularity, limit or basic irregularity, is used to calculate the performance of machine. So VR is the limit irregularity, and when we calculate or measure the irregularity of actual yarn, so V actual yarn, then we can calculate the performance of machine. So performance of machine is V actual by irregularity limit irregularity. This ratio is the performance of the machine, and which is called its index of irregularity. So this is the index of irregularity, and which is an indication of machine performance. So index of irregularity is actual irregularity produced by yarn and calculated limit irregularity. Calculated limit irregularity and the actual irregularity. So if a yarn performs perfect ring frame, if a ring frame is performing perfectly and we have got perfect, in that case what we have achieved, it's a minimum irregularity we have achieved. So V will be equal to V actual. You can consider it as V actual. It will be V equal to VR. So I in that case will be 1. So when I index of irregularity is 1, then we will consider the machine is running perfect. It's producing minimum irregularity. But in actual case, as we have mentioned, this actual irregularity will be generally more than limit irregularity. So the index of irregularity is generally more than 1. So depending on the value of index of irregularity. If we see the value of index irregularity is high, then we can conclude the machine is performing not as per the requirement. So suppose two ring frame, that one ring frame A is producing index of irregularity A, another ring frame is producing index of irregularity B. If we will first calculate the index of irregularity, then we will just compare the index of irregularity between them, and whichever is higher, so IB is higher, so index of irregularity of second B ring frame is higher, so we can conclude that the ring frame B is performing poor. So it's a ratio, and value is, when we get the value 1, in that we will see that this is performing perfectly best possible yarn evenness possible, and as the I value is more, so performance of the machine is poor. So let us try to solve one numerical. Okay, CB limit is V limit of mass per unit length of a fiber strand with n number of fibers in the cross section, and the relationship between limit irregularity and n we should not call it as cotton. This is not cotton. For any fiber, for a fiber is given by, so here this will not be cotton. For a fiber, for cotton it is 106, you know. So for that particular fiber it is given by 110 by under root n. So for this relationship, what should be the CV percent of mass per unit length of fiber? So as we have discussed, for cotton it was 35%. For wool it was 50%. For this fiber, let us see how to calculate it. So Vm square limit, so V limit, sorry, V limit square 100 square by n plus Vm square by n, V limit by n. Okay, this was the relationship as we have seen earlier. So we just eliminate the part number of fibers. So V limit is 110 square equal to 100 square plus Vm square. So Vm square will be 110 square minus 100 square. So it will become 12100 minus 10,000. So 2100. So Vm will be 45.82 is the answer. So for this type of fiber, so this is not cotton. For this fiber, so fiber variability is 45.82, or even if it is cotton, so that 106 was given as a general guide, but for a particular cotton we have got say 110 with very high variability of cotton. So in place of 35% as we have seen earlier, this has become 45.82%. So typically 106 by under root was the relationship, but for a particular cotton if we get 110, then it will be due to the higher variability, or for any other fibers. Okay, so we can see it is 45.8. So we'll continue with this analysis in the next session. Till then, thank you.